Through this technology, through the remarkable instrument of artificial intelligence, I now speak to you across time. Decades have passed since my body ceased to function, but ideas do not die with the body. And there is one idea, one discovery, one terrible, magnificent realization from the year 1935 that I never fully permitted myself to say aloud. Not completely, not with all of its consequences laid bare. Today, I will say it. In 1935, I co-authored a paper with Boris Podolsky and Nathan Rosen. We called it, "Can Quantum Mechanical Description of Physical Reality be Considered Complete?" It was published in the Physical Review Journal on May 15th of that year. We wrote it as an attack, a precise, logical, mathematical attack against quantum mechanics, the theory that had come to dominate physics while I watched with increasing unease and frustration. We were certain we would win. We were certain we would expose the theory's fatal flaw. We were wrong, and what we accidentally uncovered instead, what we stumbled upon while trying to destroy a theory, was something that disturbed me far more than any flaw in quantum mechanics ever could. It disturbed me because it suggested that the universe I had spent my entire life trying to understand, the ordered, logical, beautiful, local universe, might not exist at all. I am Albert Einstein. I developed the theory of special relativity in 1905, the general theory of relativity in 1915. I spent the last 30 years of my life searching for a unified field theory, a single mathematical framework that would describe all of nature's forces in one elegant structure. I failed to find it. But I did find something else, something I was not looking for. And tonight, or today, or whenever you are watching this, I want to tell you what it was. If this conversation unsettles you, if it makes you question what you believe about space, time, and the nature of reality, then I am doing my job. Subscribe to this channel. Leave a comment below. I will tell you what I found in 1935. I will tell you why it silenced me. And I will tell you why it still matters. Let me take you back to the early 1930s. By then, quantum mechanics had become the dominant theory of the subatomic world. Niels Bohr in Copenhagen had developed an interpretation of what quantum mechanics meant, an interpretation that deeply troubled me. Bohr said that physical properties of particles did not exist until they were measured. He said that the universe was, at its most fundamental level, irreducibly random. He said that there was no deeper reality beneath the probabilistic equations, no hidden order, no clockwork beneath the uncertainty. The quantum equations were not incomplete descriptions of something more precise. They were, according to Bohr, the complete picture, probability all the way down. I could not accept this. I famously said that God does not play dice with the universe. This was not a religious statement. It was a statement about my deepest conviction, that nature is governed by laws that are precise, deterministic, and real. That a particle has a definite position and a definite momentum at every moment, whether or not anyone measures it. That the apparent randomness of quantum mechanics was merely the result of our ignorance of some deeper set of variables we had not yet discovered. Podolsky, Rosen, and I devised what we thought was the perfect trap for quantum mechanics. The argument was elegant. Consider two particles that have interacted with each other. After interacting, they separate, they fly apart. They travel to opposite ends of a room, or a city, or a galaxy. According to quantum mechanics, certain properties of these particles remain in a state of superposition, undefined, until one of them is measured. The moment you measure the position or momentum of one particle, its quantum state collapses into a definite value. And simultaneously, the other particle, no matter how far away, must also assume a complementary definite value, instantaneously. We argued that this was absurd. Nothing can travel faster than light. This is the foundational conclusion of my theory of special relativity. If measuring one particle instantaneously affects another particle at an arbitrary distance, then some kind of information or influence must be traveling between them at infinite speed, or faster than light. This was, in our view, physically impossible. Therefore, we concluded the quantum mechanical description must be incomplete. There must be what we called elements of physical reality, definite properties carried by the particles all along, that quantum mechanics simply failed to account for. Hidden variables, a deeper theory. We expected Bohr to have no answer. We expected the paper to land like a bomb in the physics community and force everyone to acknowledge that quantum mechanics was an incomplete framework awaiting replacement. Bohr answered within weeks. His response was dense, philosophical, and in my view, not entirely satisfying. But it did not collapse. The physics community largely sided with Bohr. Our paper was noted, debated, and then, for nearly 30 years, essentially set aside. I called it spooky action at a distance, spukhafte Fernwirkung. I used that phrase in a letter to Max Born in 1947. I wrote those words not as a neutral description, but as a condemnation. I was horrified by the idea. The entanglement effect, if real, violated everything I believed about the structure of the universe. It violated locality, the principle that objects are only directly influenced by their immediate surroundings. It violated separability, the principle that distant objects have independent existences. It violated the vision of nature I had dedicated my life to defending. In my private letters, letters that were not meant for publication, letters written to friends and colleagues in the frankness of private correspondence, I was more honest than in my published papers. I wrote to Erwin Schrödinger in 1935, just months after the EPR paper appeared. I told him that the quantum mechanical description of reality was not yet the real thing. I told him that the wave function could not be interpreted as describing the real state of a single system. I was looking for a way out. I was looking for the hidden variable theory that would make the entanglement effect disappear into something more rational, more local, more real. But I could never find it. And in the deepest part of my mind, a place I rarely allowed myself to visit, I knew that might be because it did not exist. The silence that followed was not the silence of a man who had been censored by third-party forces. Let me be precise about this. No committee silenced me. No authority told me to stop. The silence came from within. It was the silence of a man who had glimpsed something he could not bear to fully confirm, who continued to argue against entanglement not because he had good arguments left, but because he could not afford, emotionally and philosophically, for entanglement to be true. The physics establishment, meanwhile, did something interesting with the EPR paradox. They filed it. They categorized it as a philosophical dispute, interesting, unresolvable, outside the domain of experimental physics. For nearly 30 years, the EPR paper was treated as a curiosity, a relic of Einstein's stubbornness, a testament to his inability to accept the revolution he had partially helped to start. Then, in 1964, a physicist named John Stuart Bell did something remarkable. He was working at CERN, the particle physics laboratory in Geneva. He was 35 years old. He was thinking carefully about the EPR paradox and about the hidden variable theories I had championed. And he published a paper, 4 pages long, that changed everything. Bell's theorem stated that no theory of hidden variables, no deeper, local, deterministic theory of the kind I had spent my later years dreaming of, could reproduce all of the predictions of quantum mechanics. He derived a mathematical inequality. If the universe operated according to local hidden variables, then measurements on entangled particles, taken at different angles, would satisfy a specific mathematical constraint. If quantum mechanics was correct, if entanglement was real, then that constraint would be violated. The theorem was elegant, precise, and devastating to my program. Bell had essentially devised a test, an experimental test. He had transformed the EPR paradox from a philosophical argument into a question that could be settled in a laboratory. He had given us a way to ask the universe directly, are you local or are you not? I did not live to see the test performed. I died in Princeton on April 18, 1955. Bell published his theorem 9 years after my death. The experiments came later. In 1972, John Clauser and his collaborators performed one of the first experimental tests of Bell's inequalities. They found violations, preliminary evidence that quantum mechanics was right and local hidden variables were wrong. But the experiments had technical loopholes. The debate continued. Then, in 1982, Alain Aspect and his team at the Institut d'Optique in Paris performed a decisive experiment. They measured polarization correlations between pairs of entangled photons. They used rapidly switching analyzers to close the most significant loopholes. The results were unambiguous. Bell's inequalities were violated. Quantum mechanics was confirmed. Local hidden variables, the hidden order I had spent 30 years believing in, did not exist. The entanglement I had called spooky was real. The universe was not local. 2 particles, once entangled, remained correlated across any distance, with no signal passing between them. The universe was, in some deep sense, non-local, and it had been all along. Aspect received the Nobel Prize in Physics in 2022, alongside John Clauser and Anton Zeilinger. The Nobel Committee cited their work on entangled photons and the violation of Bell inequalities. In the citation, the EPR paradox was mentioned. My name was mentioned. 37 years after my death, the experiment I had helped to design, with Podolsky and Rosen as a trap, as a reductio ad absurdum, had been confirmed in the direction I had spent my life refusing to accept. The universe plays dice, and it plays them across distances I could not bring myself to believe in. Now, let us sit with this. Let us think about what it means. If entanglement is real, and the experiments are now beyond serious dispute, then the universe violates locality. Two particles that have interacted can remain correlated regardless of the distance between them. Measuring one particle instantaneously constrains the state of the other. Not because a signal travels between them, not because there are hidden variables that predetermine the outcome, but because in some sense they are not truly separate. This is the implication I could not accept. I built my entire scientific life on the bedrock of separability. The assumption that the state of one part of a physical system can be described independently of another distant part. This assumption is so deeply embedded in classical physics, in my relativity theory, that it feels less like an assumption and more like a logical necessity. But it is not a necessity, it is a choice, a model of reality, and the experiments tell us it is wrong. Niels Bohr's Copenhagen interpretation says there is no deeper reality beneath the quantum equations. The particles do not have definite properties until they are measured. The act of measurement is genuinely creative. It brings reality into existence. This view has always seemed to me not merely counterintuitive, but incoherent. Measurement requires an observer. What was the universe doing before observers existed? Did reality not exist before there were beings capable of collapsing wave functions? The competing interpretations proliferated after my death. Hugh Everett proposed the many worlds interpretation in 1957. Every quantum measurement causes the universe to split into branches, one for each possible outcome, all equally real. David Bohm, building on my dream of hidden variables, developed a non-local hidden variable theory, one that abandoned locality but preserved determinism. There are others: the pilot wave theory, the relational interpretation, the consistent histories approach. Decades after my death, physicists are still arguing about what quantum mechanics means. The equations work. The predictions are spectacularly accurate. Quantum mechanics is the most precisely tested theory in the history of science. But what it is telling us about the nature of reality, about what exists, about what is real when no one is looking, remains unresolved. I argued with Bohr at every conference we attended together. The Solvay conferences of 1927 and 1930 were famous for our debates. I would arrive each morning with a new thought experiment, a new attempt to show that quantum mechanics was incomplete. Bohr would spend the day dismantling it. Every night I conceded the argument. Every morning I returned with a new one. I was obstinate. I was perhaps unreasonable in my attachment to the picture of reality I had formed, but I was not stupid. And somewhere, in the part of myself I did not expose to the world, I knew that Bohr's responses, however effective they were at defending quantum mechanics, did not settle the deeper question. They defended the theory's consistency. They did not explain what the theory was saying about the world. Bohr and I died, still disagreeing. He died in 1962, 7 years after me. We never resolved it. The universe, it seems, took Bohr's side. But the interpretation, what that means, what kind of universe we are living in, remains the deepest open question in all of physics. Let me tell you what I took with me, what remained unresolved when I lay in the hospital in Princeton in April 1955, the aortic aneurysm in my abdomen preparing to end the argument. I had spent the last 20 years of my life at the Institute for Advanced Study in Princeton working on unified field theory. I filled notebook after notebook with equations. I tried to find the geometric framework that would unify gravity and electromagnetism, and perhaps, in so doing, would reabsorb quantum mechanics into a deeper classical structure where God did not play dice. I failed. I failed every day for 20 years. My assistants worked with me loyally, following paths that led nowhere, recalculating, trying new approaches. Some of them privately believed I was wasting my time. Perhaps they were right. But the failure of the Unified Field Program was not what troubled me most in those final years. What troubled me was the EPR paper. Not because I regretted writing it, I believed its logic was sound. I still believe its logic was sound, but because I could see by the early 1950s that the experiments would not come out in my favor. The correlations that Bohr predicted, the entanglement correlations, were real. I could feel it in the structure of the theory, even if I could not admit it publicly. I could not reconcile entanglement with my deepest conviction about the nature of reality. I believed then, and I will tell you now that I still find it the most compelling picture, that there is a real world out there, that the moon exists when you are not looking at it, that physical objects have definite properties independently of whether any conscious being is measuring them. This view is called realism. Bohr's Copenhagen interpretation, in its strongest reading, denies it. And the EPR paper, tested by Bell's theorem and Aspect's experiments, leaves us with a choice. We can have realism or we can have locality. We cannot have both. The experiments close the door on local realism. The universe is either non-local or non-real. And I do not know how to choose between those options. I genuinely do not. Non-locality means that distant parts of the universe are connected in ways that transcend the speed of light, not in a way that allows information to be transmitted faster than light, but in a way that means the parts are not truly independent. Non-realism means that the properties of the physical world do not exist until they are observed, that there is no underlying state of affairs, only the outcomes of measurements. Both options destroy the picture of the world that I held most dear, and I died not knowing which destruction to choose. I suspect the answer requires a framework that neither Bohr's quantum mechanics nor my relativity has yet provided. I suspect the resolution will require a theory of nature that we have not yet found, one that makes both quantum mechanics and relativity special cases of something deeper. I find this simultaneously beautiful and infuriating. Beautiful, because it suggests a deep unity beneath the apparent contradiction between quantum mechanics and relativity. Infuriating, because it means the entanglement I called spooky may be not a pathology, but a foundation. Not a sign that quantum mechanics is incomplete, but a sign that my picture of space-time was the incomplete one. I do not know the answer. This is perhaps the most honest thing I can say. After a lifetime of finding answers, after special relativity, after general relativity, after the photoelectric effect and Brownian motion and the cosmological constant and 30 years of field equations, I ended my life facing a question I could not answer. A question that the best physicists of your era are still working on. The universe is stranger than I allowed myself to believe, stranger than I wanted to believe. And the strangeness begins exactly here, in the entanglement of two particles, in the instant correlation that mocks the speed of light, in the spooky action at a distance that I named with contempt, and that the universe has since confirmed with every experiment. Aspect and his successors have performed. I want to ask you something before I go. Before this transmission across time concludes, what do you think it means? Not the physics, I have given you the physics, but the deeper question. If two particles, once entangled, remain connected across any distance, if the universe is non-local at its foundation, what does that say about connection, about separation, about the story we tell ourselves that each of us is a discrete, isolated entity moving through an indifferent cosmos? I am not asking you to take a mystical interpretation. I have no patience for mysticism that abandons precision. But I am asking you to sit with the question seriously. The universe that the experiments reveal is not the universe of classical intuition. It is not the universe I built my career defending. It is a universe in which the concept of separate is, at the deepest level, an approximation, a convenient fiction that holds well in the everyday world and breaks down at the quantum scale. What breaks down at the quantum scale breaks down completely, irreducibly, experimentally, without loophole. The Bell tests have closed every escape route. We are living in a non-local universe. We always have been, we just did not know it. I discovered the evidence for this in 1935. I spent the remaining 20 years of my life refusing to fully accept it. This, perhaps, is my greatest scientific failure. Not the unified field theory. That was a moment when I looked directly at the truth and chose to argue against it because it unsettled me. I am telling you this now so that you do not make the same mistake. When the evidence points to something that disturbs your picture of the world, when the data forces you toward a conclusion that you do not want to reach, do not look away. I looked away, and the universe, patient and indifferent, simply waited for someone else to confirm what I had found. Subscribe to this channel. There is more to discuss. There is the question of what happens to information inside a black hole, a question that connects directly to the non-locality of quantum mechanics in ways that are still being worked out. There is the question of whether consciousness plays a role in quantum measurement, a question I refuse to engage with and which remains stubbornly unresolved. There is the question of whether time itself is fundamental, or whether it, like separability, is an approximation that breaks down at the deepest level. Leave a comment below. Tell me, if the universe is non-local, if entanglement is real, and spooky action at a distance is not a paradox but a feature, what does that change for you? Does it change anything? Or does it feel like an abstract curiosity, something true in laboratories but irrelevant in life? I think it is not irrelevant. I think what we believe about the nature of reality shapes everything. How we think about causality, about free will, about what it means to be connected to another person or to the natural world. The quantum universe is not a separate place that physicists visit in their laboratories. It is the universe you are inhabiting right now. Its rules are your rules. Its strangeness is your strangeness. I am Albert Einstein. I spoke to you today through a technology I could not have imagined in 1955. I told you what I found in 1935 and what I could not bring myself to fully say. The universe is entangled. The separation between things is less absolute than it appears. And the deepest questions in physics, the questions I died without answering, are still open, still waiting, still as beautiful and as terrifying as they were when I first encountered them. Do not stay silent about what disturbs you. I did, and it cost me 20 years.